In this video, we are going to take a look at how to represent certain types of functions as power series. As it says in here, being able to represent a function as an infinite polynomial is a powerful tool. And so that's what we are going to be doing in this section and the next couple of sections is we're going to see how we can take a function and represent it as an infinite polynomial. So what these problems have in common now in exercise 3 is that they can all be written similar to the sum of a geometric series. So I'm going to start off here by taking a look at geometric series. So this is the function 1 over 1 minus x that we're concerned with now. And so right here I have a geometric series. The sum from n equals 0 to infinity of a times r to the n power. And if we write out the first few terms of that series, we have a plus ar squared plus ar cubed, all the way up to a plus r to the n. Now, we learned once upon a time that the sum of that geometric series is in the form of a over 1 minus r. And quite often a is just 1. If we were to let a be equal to 1, we would have it in the form of 1 over 1 minus r. And so going back to our function now, you notice that the function looks an awful lot like the formula for the sum of an infinite. This is the sum of an infinite geometric series. So the sum of an infinite geometric series is a over 1 minus r, or if a happens to be 1, as it is in this case, 1 over 1 minus r. So our function looks like the sum of an infinite geometric series. And so that's our starting point here. And so we know that this infinite series converges to 1 over 1 minus r when the absolute value of r is less than 1. So here's what we're going to do. We are going to take and let a be equal to 1 and let r be equal to x. And when we do that, we're going to go back to our geometric series and replace a with 1 and r with x. And we get something that looks like this. The summation from n equals 1 to infinity of x to the n. And that is our infinite series. And so if we write out the first few terms of that series, we have 1 plus x squared plus x cubed, And we would then know that the sum of that infinite geometric series is going to be 1 over 1 minus x. So the function is the sum of an infinite geometric series. And so the actual series representation of this function would be this. Now, this might be a little bit abstract to kind of wrap your head around as to what exactly is going on here, but the idea with these problems is that we want to make the function look like the formula for the sum of a geometric series. And so the next one, oops, there we go. The sum of the geometric series. Now, can't read it. This is f of x is equal to 1 over 1 plus x cubed. So a is equal to 1, which I have written right here. A is equal to 1. And we have to make 1 plus x cubed. We have to make 1 plus x cubed look like 1 minus r, the denominator of our formula. Okay? The denominator of the formula for the sum of an infinite geometric series. And so we know that plus a term can be written as minus the negative of that term. So if we was to write 1 minus negative x cubed, we would then have it in the form of 1 minus r, where r is then equal to negative x cubed. So just a little algebra there. So now that we have r and a, we can actually write our series. And so the series would look like this. So A is 1, so we basically just have a 1 out here. So remember how to write a geometric series. It's A times R to the n from n equals 0 to infinity. And if you wanted to write out a few terms, you could write out a few terms of that alternating series right there. Now, to determine whether the series converges and what it converges for, basically you can use the tests that we've been using. I've kind of skipped over a bunch of that, but we can then test this particular series to determine what its interval of convergence is, what its radius of convergence is, and we could do that using the techniques that we just learned in the previous video. And finally, one more. So we have this. So the challenge here with that is to make that look like the form, the sum of the infinite series is a over 1 minus r. So it's the denominator that doesn't look like it. We need to take 4 minus x squared and make it look like 1 minus the radius. And so I do that here. First, start by factoring a 4 out of the denominator. And when you factor a 4, so you have 4 minus x squared, that becomes 4 times 1 minus 1/4 x squared, which you could write as 4 over 1 minus x over 2 quantity squared. And so the 4 we don't need. We don't want that down here. We just don't want a 1 minus r. So the 4 down here can go up into the numerator as 1/4. Okay? Because 4 in the denominator is the same as 1 over 4 in the numerator. So that's how we get rid of that 4 in the denominator. And so that's where we get this 1 minus x squared. So the 4 goes away, goes to the numerator, and we end up with 1/4 x squared over 1 minus x over 2 quantity squared. And so in this particular case then, we see that a is equal to 1/4 x squared, and r is x over 2 quantity squared. And so creating our series from that, we would have something that looks like that. And simplifying that a little bit, we get something that looks like that. And so I'll let you play with that, but you should be able to figure out how we went from here to here just by manipulating the exponents. Because remember, 1/4 x squared is just x squared over 4. Okay, and so this becomes our series, and here are the first few terms of the series, and then you can test it to determine what the interval and radius of convergence are. But the important thing here is to be able to take a series take a function like x squared over 4 minus x squared and represent it as a power series. This is called the power series representation of a function, and we will be doing more of this for lots of different types of functions.